Welcome. In this video, I will be continuing my series on functions. In the last video, I defined functions as broadly as imaginable. I allowed the domain and the codomain to be any sort of object. There's a slight problem with that, which is that it's really hard to do mathematical analysis on random objects like this. All right? So I want to kind of restrict our perspective a little bit to be able to allow us to do a more nuanced analysis. And I'm going to be doing it in the setting of creating a probability function. All right? So for a probability function, I need a probability space. I need a sample space, and I need an event space. You can check the section on probability theory. And my sample space here is going to depend on the random experiment that I'm going to be performing. Well, the random experiment is going to be, I'm going to select one of these books by random. All right? So each of these books is an outcome in my sample space. And the notation for the sample space is capital omega from the Greek alphabet. All right. Then a subset of the sample space is going to be an event. So some method of selecting some of these outcomes is going to be called an event. And saying I want to choose a blue book is an event. That is the event that consists of these three books. A green book is these three books, a yellow book is these four books, and then a red book is these two books. So what I've actually done here is that this thing here is actually a part of the event space. I think this is the notation. So all these colors are actually a part of the event space. All right, beautiful. Okay, so to calculate the probability, usually the first step to calculating these probabilities is to count. To count how many elements, outcomes, there are in these different events. But we already did this, remember? When we took the inverse of a color by f, we had, the inverse of f was a multi-valued function. It gave you multiple values when you evaluated at a color. And the number of values is exactly what we need here. The number of values of the inverse of f on blue is going to be the number of elements, outcomes, that have this color. So our counting function, it's called g, it's going to be the size of the inverse of f. Isn't that beautiful? We're so close to disregarding these multi-valued functions, and they're just, and here they go, saving the day. I mean, you can do without, you can just count them, or you have some other process, but I like the fact that they're helping. All right. So the question is, what is then the codomain? So our domain right now is going to be these colors. The codomain is going to be these colors. The domain is going to be these colors. So what's the codomain? Well, the codomain, when we're counting, what results can we get? Which numbers can we get? Well, objects, I'm kind of spoiler there. Well, what we have is we have the natural numbers. Those are the counting numbers. Some people don't like starting from 0, but I do. I always start from 0. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, and so forth. The reason I went to 12 is because I have 12 books here. Okay, beautiful. So what does this counting function do? Well, like always, we can draw our lines. If we have no other way of expressing it, let's just draw our lines, okay? I know this is 3. I know there are 3 books that are blue. So I draw a line to 3 here. Same with green. There are 3 green books. There are actually 4 yellow books, and there are 2 red books. That's it. You can see that the purple function is far from surjective. It's not even close. It takes 3 other values and ignores all the values. You could remove the other values, but I feel like there's some value in actually in keeping the others, because it kind of shows the possible values and what you didn't use and so forth and so forth. So there's, as far as I can tell, there's not a big benefit to actually having this function be surjective. So I'm not going to restrict the codomain. All right. So what is the next step? And it's not injective either, because these two values have the same number. So neither surjective or injective. But I can tell you it's extremely interesting and relevant anyway. So this is just to say that bijective functions are not the only functions that we're interested in. Okay, so let's make the next connection here. Let's see if we can actually turn this into a probability function. All right. So this does not represent the probability. This is just a counting function. To actually get the probability, we need to get this somehow into the 0, 1 interval. We need to make this interval that goes from 0 to 1. Okay, and the way you can do this, we can pick up the line here, and we can do a line approximately here. All right. So this is this line from 0 to 1. Okay. All right. And then I can just draw a new line. Right. I can go, well, 4. What is the probability, if I have 4 yellow books, what's the probability of picking out a yellow book? Well, there are 12 books total. It's 4 out of 12. Okay? That's a third. So that's 1/3 of this whole line. It's actually, let's put it approximately here. Okay, what about 3? Well, 3 out of 12, that's a quarter. Okay. I actually cheated a little bit here. That's why I wrote up 12 here. So this, all these numbers actually go straight up to that point on the graph, on the line. All right. So then I have this function. Let's call it h. And what h does is just converts the count to a probability. All right. So we have 1/6 here. We have 1/4 here, and we have 1/3 here. Beautiful. How do we now get the ultimate probability function here? Well, we can simply take these two functions, and we can compose them, just like we did earlier. So if I want the probability function, what I need to do is I need to take h and compose with g. So I take h and g, and I compose these. And what this function does, it goes from the colors, which is the event space, and it goes into the interval from 0 to 1. And when I make a composition like this, what I'm really doing, I'm just starting from each of these, and then I'm following these lines up. Following this line up here. Doing the same thing over here. Following this beautiful little line up here. And then this last will be over here. So the blue probability function is actually represented by these lines that start down by the colors, go through the counting numbers, the natural numbers, and end up here at the 0, 1 interval. Yes, isn't that beautiful? So we started with something super abstract and kind of useless, to be perfectly honest, to something that's actually pretty useful. And what it really took is, it took changing our codomain into something that is more mathematical, into these numbers, because then we can start doing mathematical analysis on these numbers. All right. This is, I think it's beautiful, but it's slightly cumbersome, and it takes up a lot of space. Like, this, I don't want to do this for every function if I can avoid it. So what you can actually do is, you can look at this function. You can look at h. And what did I do to calculate x? Well, I made these vertical lines. But what was really happening is I was actually just taking these three numbers and I was dividing by 12. That's it. So what I can do here is, let's say I remove one of these books. So it's, for example, I remove one of the blue books, so it goes over here. Or I remove two of them, or remove one of the red, so I get one red book, or something like that. Let's just say I change the number of books, or the different distribution of colors, so I get other numbers here. I still want to be able to handle this without having to manually draw these lines again. And how I can do that is, I can take this h function and I can represent it as with a functional expression. And what I did is I took one of these numbers and I divide by 12. So instead of taking every single number here and drawing a vertical line up here, I mean, it takes time, it takes space, it takes energy. A computer would have a hard time actually dealing with this because it's very hard to automate this process. But this, look how beautiful this, how compact this is, how easy this is. And in the previous video I mentioned a machinery analogy, and this is what it is. A lot of teachers will actually define a function as this machine that takes in an input from the domain and spits out something from the codomain. But a lot of functions, most functions I would argue, do not have this nice way of converting from the domain to the codomain. But if you have a function that has this property, it's really nice. It's way easier to handle. It's very much easier. But what it really is just a convenient way, a shortcut to all these lines, to all these relations that we've already speaking about. So this is by far my favorite way to represent a function, absolutely. But it's not the only way, and is not at the core of what a function actually is. Beautiful. So when I have this, I actually have another way to express my probability function. So the probability function actually ends up being, if I can take the probability of a color C, then it's going to be, I'm going to take h of g of the color. Well, if I want to do h, the process of doing h is taking the thing that it's in taking the value from the domain and dividing by 12. So this is going to be the same thing as g divided by 12 of the color. And we've also shown that g also technically has an expression right there, which is the inverse of f, oh, this should be probably orange, inverse of f on the color. We take the size of this and then we divide by 12. Which is incidentally the size of the sample space. So we've created a probability function from these three separate functions, where the first function was a completely abstract function from a random set of objects to another random set of objects. The second function was a function from which had a domain of completely random objects or non-mathematical objects, but now we introduce this mathematical structure here. And then at the very end, we have this h function, which is even nicer. It goes from a mathematical structure into another mathematical structure, which allows us to do this really nice representation of the relation. All right. This way to represent the function is not the only benefit it's not. The only benefit of this is not that it's more compact and more convenient. There's another benefit to it, and that benefit is that we can represent this domain and codomain graphically in a more systematic way than we've done before. For example, we can make so-called axes, and we can put 1, 2, 3, 4 out here, and then we can represent the value associated to each of these on this vertical y-axis. So we can go, okay, cool. This is 1/12, this is 2/12, this is 3/12, this is 4/12, 5/12, and so forth. And this is, in my opinion, a way more intuitive, way more informative visual representation of the relationship between the counting numbers and the probability. So you can see how it increases. Actually, it increases by a 12th, and that is actually something defined as the slope, sort of. Beautiful. Okay. So what we've done here is we've gone from the super abstract and non-mathematical to the more mathematical functions by just changing the domains. And we've seen that there are a lot of benefits. And this is why you will really rarely, you will never work pretty much with functions that are defined like this. It's possible, but it's very impractical. You will, in some certain circumstances, work with functions that are defined like this, on random non-mathematical objects, but where the codomain is actually a mathematical object, where we can do some useful operations on it. But by far, this is more common, where we're going from mathematical structures to mathematical structure. And the next step, which I will not do in this video, is actually where you do not have these discrete functions. A discrete function is a function that goes where the values are separated by some value. Where we actually have functions where we allow every single value in between. All right? For example, how this can be achieved is by taking the width of these books. If you don't count the books, but we take the width of the books, and the probability of getting that book is the width of that book, then a book can have any width. And that can really lead to any probability. And that means we start filling out way more of this instead of just taking these discrete values. Next step is then to take these continuous structures and then take a function into another continuous structure. And then everything will be even nicer than this. And that's where we'll spend most of our time. And that's going to be the next video. If you have any questions or comments, leave them below.